So now what we want to do is, we want to see what happens when we do the opposite. What is the opposite? You declare a function, okay, with, let's say, 3 arguments. Okay, so let me go back here. And I will say this guy is int comma int. Okay, and now what am I going to do? I will pass, of course, if I leave it at this, you will get a compiler error because I am calling it with only 1 argument but declared it with 3 of them. So I will do y and I will also send y to this, okay, or maybe 2 into y. Let me do this for variety, right? So I am going to call this function as f1 of 20, then some 100 and 200, okay, and I am going to now allow this function to execute in this thing, right? So what is going to happen? So let me change this guy here, 50, okay. So of course it is obvious that what I am passing as 2y is not even getting used in this function. This function does not even know about this, okay. So what is the expected answer, by the way? So we will come to that in some time, but effectively you are doing x into y into some macro val. So this 200 does not seem to be getting used, okay. So we will see why that is the case in the next example. So what we want to do now is to understand what happens when I pass more parameters, right? So again here I am going to go back to the same simple function fn that we had. I have declared it now with 3 parameters here, int comma int comma int, right? And in the main I am obviously calling it just like on the Godbolt example. I am calling it with 3 parameters, 2, 4 and 8, right? And the assembly will get translated like this. So what is the assembly translation? You start with a prolog of main, move EBP minus 4, that is basically z equal to 0 as usual. Now this is the function call fn of 2 comma 4 comma 8. So this argument is what is getting, right, it's getting pushed right to left. So push 8, push 4, push 2 and then you are calling fn, okay. Now of course the other function, as object code of the function fn remains the same because we have not rewritten that at all. Assuming that's in a different file, that object code could have been compiled and just kept aside once. All we are doing is changing the file that is containing the main, how you call this function, right? So therefore again what are we going to do? Here is the function main, okay. We are assuming that you have executed all this part of code, right? We have executed all this and now we are waiting at call C200, where C200 is where fn resides, right? Fn address again is 0xC200, right? Now you note that we have earlier the call was residing in address C103, but now we are doing C104 because this because we are now pushing this extra parameter, okay, and therefore it's that address is obviously going to change, right? So now what we do is the stack picture is shown on the right, for you at the point when the call C200 is executed, okay. C104 is where the call instruction resides in the code segment. C105 is where the next instruction. So when the call is being executed, C105 is the next address of the next instruction that gets pushed onto stack, right? And you move ESP up, or rather you subtract 4 from ESP. Then what do? You load the instruction pointer with C200. So this is where the EIP basically gets initialized to at this point, okay. Now this is the picture of the stack. And now what are we going to do? We are going to go ahead and execute this program exactly as per the assembly instructions shown here starting from C200. So you push EBP, so the EBP of main goes there, then you move EBP comma ESP, so whatever the value of ESP is, you put that into EBP, so the EBP gets initialized now to the stack of the function fn. Then what do? You subtract ESP comma 0x40 local variable space, you move 0, initialize the local variable z in fn to 0, then you do move EAX comma EBP plus 8. Now you watch what happens. EBP plus 8 is this guy. This is my EBP plus 8, right? What is this? This is EBP plus 12. What is this? This is EBPP plus 16, right? But this function fn does not know that it is going to be called with 3 parameters. So it assumes that there are only 2 parameters that it is going to deal with, and therefore it is going to only deal with EBP plus 8 and EBP plus 12 in its object code. That's what you see here, right? So therefore when you execute this, what is going to happen? My EAX will get 2 plus 4 from EBP plus 8 and EBP plus 12, which is 6 as the answer. Then I move EAX, so 0x006. So therefore now the answer that goes into Z is indeed deterministic. It is not some random garbage value, because I have not even accessed any random space. I am accessing exactly the parameter space of the function fn. Okay, and what is being done is what was pushed as the third argument, as this 2 into y, right, or whatever there that we had, right, or that is on the Godbolt side. Here we pushed 2, 4 and 8, correct? That 8 is being ignored completely because it is not being used in the function, right? So now what do I do? I do add ESP comma 0x40, undo the local variable space allocation, pop EBP, get the EBP back to where it was. Then you do ret 8. Okay. So what do you do? So when you do ret 8, again what happens? In 2 steps I am showing it, but in hardware it happens in one shot. Top of stack is popped into EIP. So this is the return address of this guy. So EIP has to come back here. So you do this and you see the black arrow is back there, right? And then my ESP is going to get added with 8 because I did ret 8. So ESP is pointing here. Okay. Now what do? I say move EBP minus 4 comma EAX, right? Yeah. So what I'm basically going, so what happens here is, I continue executing move EBP minus 4 comma EAX. That value, EAX value is 6, which is correct, right? The x and y that we passed, 2 and 4 are exact values. You get the answer 6, and then you go ahead and return from this program. Now what is going to happen? The problem here is my ESP is actually still not back to its original value. Okay, remember when we started all this when we started doing all this from main, right? My ESP was in a certain location, but even now what we have done, we have pushed more parameters, but not undone the pushing with the same number. Okay, so we have pushing is going to subtract ESP. We did 3 pushes of 4 bytes each, it would have subtracted ESP by 12, right? But when we did ret 8, ESP is going to get added with 8, and therefore there is a mismatch of 4. And even now what will happen is when you finish main and exit and return, the top of stack is not going to point to the return address of what called main, because there is a mismatch now, and therefore you will still return to a absolutely incorrect point and your execution flow will be messed up. So what we have done now is, by passing more parameters, we have no illegal access of the stack. Okay, the function fn is not accessing the stack of the calling function incorrectly. That we have gotten rid of. However, because we pushed 3 parameters but accounted only for 2 of them in the ret with ret 8, there is a mismatch and that is still a problem. Okay. So that's why what we need to do now is we need to fix this problem. Okay, we need to fix this problem. And how do we do this? Because the function fn, if it assumes that it is always going to get 2 parameters, then you cannot pass different number of arguments, even though passing more arguments seems to be working okay without any illegal stack access, right? And therefore, what we are going to do is we are going to recompile this function fn with a slight modification. Okay, what is the modification? So push EBP, all this is the same, right? Then move EBP, ESP, allocate local variable space, initialize the local variable z to 0, then you add 2 and 4, that's 6 sitting in EAX, write the value 6, then you add ESP, 0x40, pop EBP. Finally, when you come to the return instruction, you don't do ret n, you just do ret. Okay, so what is the advantage with this? The advantage is it is not trying to do the stack cleanup. Stack cleanup is adding ESP with some offset so that you correct for parameters that were pushed onto stack. But by doing an RET, this function is saying, look, I do not know how many parameters my function has been called with, and therefore I will just do RET, right? So when you do RET, you just bring the ESP back. Now what you do at C105, and note this instruction, it is not the move, this is not z equal to fn, whatever, right? This is not the assigning the return value from EAX to z, but instead what we are doing, we are inserting one more instruction called add ESP, 12. So this is what is doing the stack cleanup. This is exactly what is taking care of the stack cleanup very correctly now. Why? Because in this function main, when you call this function, you called it with 3 parameters. And therefore, after you return from this function, you know you have to clean up for 3 parameters, and that's why you are doing add ESP, 12. The compiler, when it looks at this code, it sees you are passing 2, 4, 8 integers, which means I have pushed 4 bytes, 4 bytes, 4 bytes. I need to clean up those 12 bytes, and therefore I will be able to do this add ESP, 12 appropriately and thereby correct and clean up the stack exactly. So now what happens? I bring my ESP back here and undo all the pushing that was done, right? And then I do all the, whatever remains in the main, and then when I do the epilogue, ESP will now go back to its correct position so that you finish up, you take care of returning to the correct address when from after main has been executed. Okay, so like I said, the OS calls main, so this return address has to go back to the OS exactly at the point where the call was made, right, or after the call was made. That address will be correctly taken care of because we have done the stack cleanup correctly. So here we have not only taken care of illegal stack access, we have also taken care of correcting for the parameters which have been pushed, and in fact very specifically more parameters that have been pushed, because we know the exact count in this case. So that brings us to the idea of a calling convention, right? What is a calling convention? A calling convention, basically there are 2 types of important calling conventions that are used in Windows. One is an __ cdecl call, right? This is the default calling convention for all C functions in MSVC. This is needed for variable argument list functions, okay, where you do not know, the function does not know how many arguments it will be called with. So the caller takes care of stack cleanup. So that means the cdecl function definition will just have an RET. It will not have an RETN. Okay. The add ESP comma n will be the instruction that gets executed immediately after the call, okay, of this cdecl function, because that is going to do the stack cleanup for you. On the other hand, there is an underscore std call which is faster than cdecl call. Why? Because when you do ret n, right, that returning and adding ESP with n gets done in one shot in hardware, and therefore it is faster. However, it's the callee that takes care of the stack cleanup with the RETN instruction, right? But of course, in this case, you cannot pass any arguments different from what the definition is if you want that to work correctly. Okay.